Welcome to my class. I'm Drew Collop. In today's class, we're going to continue talking about stoichiometry. Initially, we introduced stoichiometry as a recipe in the kitchen, having to mix a certain number of ingredients together to make a final product. We then moved into the laboratory and introduced the concept of a mole and molar mass. Using the molar mass, we can convert between the number of molecules to the number of moles, and then finally to the number of grams. This is important because in the lab we can't count atoms just yet. We weigh them instead. We're now going to add in chemical equations into stoichiometry. Let's get started. Anytime there's a chemical change, this can be illustrated by writing species. Notice we call them species. On the left-hand side, these are your ingredients. We don't call them ingredients, we call them reactants. So if this was your chemical reaction here, these would be called your reactants. We then place an arrow indicating a new species will be formed. And this comes on the right-hand side. We call these the products. Notice we use the chemical symbol for the elements and the compounds in the chemical reaction. In addition, we write in brackets whether or not it's a solid, a liquid, a gas, or it's dissolved in solution, aqueous. Here you can see solid carbon reacts with the oxygen molecule as a gas. It then creates the molecule carbon monoxide as a gas. If we examine closer, we will notice there's a quantitative relationship between the reactants and the products. As a result, we have to balance this chemical reaction. Let's balance this reaction now. For reactants, we have carbon, we have oxygen. For products, we also have carbon and oxygen. The number of atoms of carbon and the number of atoms of oxygen should be equal on both sides of this chemical reaction. We look at the carbon. You can see we have one carbon and one carbon, so that balances out. But if we look at the oxygen, it doesn't balance out. We have two oxygens. As a result, we have to write a 2 here. Now, two oxygens, two oxygens. We then look at the carbon now. Here is two carbons, so I have to write a 2 in front of that one. Two carbons, this is balanced out. You don't have to write it, but if you would like, you can write a 1 in front of the oxygen. We now have a balanced chemical equation. These values here, they are coefficients. As a result, they are exact values. 2 atoms of carbon react with 1 molecule of oxygen gas to create 2 molecules of carbon monoxide. Those are exact values. I could also say 2 dozen carbon atoms react with 1 dozen oxygen molecules to create 2 dozen carbon monoxide molecules. I could take it one step further. I can say 2 moles of carbon react with 1 mole of the oxygen molecule to create 2 moles of carbon monoxide. So this is where the term mole comes into play. Again, these coefficients are exact numbers. So when calculating significant digits, they are not taken into account. We can build a mole ratio for the amount of carbon to the amount of oxygen to the amount of carbon monoxide. And if we look at our balanced chemical equation, the ratio is 2 to 1 to 2. This is important because we can use these coefficients to switch between the different species of chemicals now. Let me show you. For the above equation, how many moles of carbon are required to react with 3 moles of oxygen? So I write down what I'm given. 3 moles of oxygen. I want to go from moles of oxygen to moles of carbon. What I do, I go to my balanced chemical equation now. Two moles of carbon reacts with 1 mole of oxygen. So these are the numbers I will use. 2 moles of carbon, 1 mole of oxygen. Please note, to convert between different chemicals, you need a balanced chemical equation, and B, you use those coefficients that come before the chemicals in that balanced chemical equation. Moles of oxygen cancel moles of oxygen. I'm left with moles of carbon. Here we end up with 3 times 2 is 6 moles of carbon. Significant digits now. These are exact values. As a result, we only use this one to calculate significant digits. We have one significant digit. Therefore, this is the final answer. So just to remind you, we're using the coefficients from the balanced chemical equation to convert from one species of chemical to another. Let's now add on to that game plan we've been working with. This is now the concept known as the mole bridge. A bridge takes you from one part of the land to another part of the land. The mole bridge takes you from one chemical to a different chemical. So you can see we have chemical A here, and we have chemical B here. Just like before, I can convert between grams and moles using the molar mass, and I can convert between atoms or molecules and moles using Avogadro's number. And that holds true for both chemicals. These would be the same. These would be different for chemical A versus chemical B. Finally, we can use the mole ratio, those coefficients from our balanced chemical equation, to switch from moles of A to moles of B, or vice versa. I would advise you to print this off and have it nearby while you're learning to do chemical conversions, stoichiometry. It will help you organize your thoughts. Let's try an example now. How many moles of ammonia gas, right here, will be produced by the complete reaction of 1.92 moles of hydrogen gas with excess of nitrogen? So I'd like to find out how many moles of ammonia gas is created when I react 1.92 moles of hydrogen with an excessive amount of our nitrogen gas. When we talk about something in excess, you can imagine an infinite amount of the nitrogen here. It's in excess, meaning it is not the limiting reagent. Let's devise a game plan here. We're going to go from moles of hydrogen to moles of ammonia. I only need to do one step. I just need to move across my mole bridge that way. So what I'm going to do, my plan, is go from moles of this to moles of that. Let's write it down. I've been given 1.92 moles of hydrogen. I'm now going to convert from moles of hydrogen to moles of ammonia. The question is, what numbers go in here? We need to balance the chemical equation first. Notice we have 2 nitrogens, 2 hydrogens. Here we have 1 nitrogen and 3 hydrogens. Let's first balance the nitrogen. If I have 2 nitrogens here, I can balance it by putting a 2 in front of my ammonia. Now my nitrogens are in balance. Now my hydrogen, notice, I have 3 hydrogens here, but I have 2 molecules total, so I need 6. To make this 6, I put a 3 in front. Now my hydrogens are balanced. And if you like, you can put a coefficient in front of the other one as a 1, just to make sure you are aware. It's 1 mole of nitrogen reacts with 3 moles of hydrogen to create 2 moles of ammonia. So we'll use our balanced chemical equation here as our conversion factor. 3 moles of hydrogen reacts with nitrogen to create 2 moles of ammonia. Those values cancel out. I'm left with 1.28 moles of ammonia. Significant digits now. Remember, these are exact values. So I have 3 significant digits, 3 significant digits. Therefore, it is in the proper number of significant digits, and that is the final answer. Again, remember these coefficients from our balanced chemical equation, they are exact values. They are not measured. As stoichiometry gets more complex, you'll have to keep track of where you start and where you want to end up. Again, I would advise you to print this off and use it while you're learning. Let's show you a more complex example now. Example 3. What mass of oxygen is required to react with 501 grams of heptane given the following equation? What do I have? I have 501 grams of my heptane, and I want to know how many grams of oxygen I need. So what I want to do is I want to switch between grams of heptane to grams of oxygen. Now we can't directly switch between the two. What we have to do, we have to use the mole bridge. So we'll go from grams of heptane to moles of heptane, and then we'll go across the mole bridge to find out the number of moles of oxygen, and finally we'll convert to the grams of oxygen. Again, let's write that out here. So here we have our heptane, where I'm starting from, 501 grams, and where I want to end up is number of grams of oxygen. So I will use the molar mass to convert from grams of heptane to moles of heptane. I will then use the mole bridge to convert from moles of heptane to moles of oxygen. And we will use the coefficients from the balanced chemical equation to do this. Lastly, I'll use the molar mass of O2 to convert from moles of O2 to grams of O2. Let's start this as a 3-step process. So we'll do the first part. We're going to convert from grams of heptane to moles of heptane. 501 grams of C7H16. I'm going to convert from grams of that to moles of that. In order to do that, I need to know what the molar mass is. Carbon, 12.01. We have 7 of those atoms. And we have hydrogen, 1.008. And we have 16 of those. Here's the respective masses from carbon and hydrogen. We're going to add those together. We get 100.198. What did I say we're going to use as our significant digits for molar mass? We're going to use 4 significant digits. So here, 1 mole, it's always 1 mole. When you're dealing with molar mass, the number goes beside the grams. It's always a certain number of grams per 1 mole. 100.2 grams goes in there. We'll do the calculation. Those values cancel out. And I've chosen a nice easy one. Gives me 5 moles of C7H16. Now please note, do not round off. We don't need to round off here. It's just 5, exactly 5. But if this number had a huge number of decimal places afterwards, please do not round off until the final answer. So now we've gone from grams of heptane to moles of heptane. Now I can convert from one species of chemical to another using the mole bridge. Let's do that now. I'm going to go from moles of heptane to moles of oxygen. I have 5 moles of heptane now. I'm going to go from moles of heptane to moles of oxygen. These values will come from the balanced chemical equation. Let's get those coefficients now. So here's my chemical equation. Let's balance the whole thing. Starting with carbon, I have 7 carbons. 1 carbon here, so I'll put a 7 on that. Carbons are now balanced. Hydrogen, there's 16 here. There's 2 right here, So to make that 16, I have to put 8 in front. 8 times 2 is 16. Now my hydrogens are balanced. Finally, oxygen. Here I have 1 oxygen. Here I have 2 oxygens. There's 8 water molecules. 1 oxygen atom per water molecule gives me 8. And with carbon dioxide, there's 2 per molecule. 2 times 7 is 14. 14 plus 8 is 22. So to balance this out, I have to make this 11. I have now 22 oxygens here, and I have 22 oxygens here. We'll put a 1 in front of that. So here I have 1, 11, 7, and 8. I'm going to be using these 2 coefficients here, going from moles of heptane to moles of oxygen. Every time 1 mole of heptane reacts, 11 moles of oxygen gas react. 1 mole of heptane reacts with 11 moles of oxygen gas. These will cancel out. And again, I don't need a calculator for this. 55 moles of O2. Again, if there were decimals here, do not round off. This is not the final answer yet. The final answer will be when we have grams of oxygen. Let's do that last step now. Going from 55 moles of oxygen, we want to go from moles of oxygen to grams of oxygen. For that, we'll use the molar mass. Oxygen has a molar mass of 16 grams per mole. There are 2 oxygens, so therefore the molar mass of O2 gas is 16 times 2. Again, 4 significant digits. 1 mole is 32.00 grams of oxygen gas. Those cancel out. Here I get 1,760 grams of oxygen. Now is the time to round. Remember, we have exact values here. As a result, we have 3 significant digits, 4 significant digits, and 4 significant digits. So this should be rounded to 3 significant digits. So we could leave it as this, or we could write it in scientific notation. 1.76 times 10 to the 3 grams of oxygen. As you can see, we use the mole bridge to convert from grams of heptane to grams of oxygen. We did it as 3 separate calculations. We determined that 501 grams of heptane was 5 moles of heptane. Using the mole bridge, we determined that 5 moles of heptane reacts with 55 moles of oxygen gas. Finally, we calculated that 55 moles of oxygen gas would weigh in at 1,760 grams. We did this as 3 different steps. Step number 1, convert from grams of heptane to moles of heptane. Remember, do not round off until the final answer. We then use that to convert from moles of heptane to moles of oxygen, and then we use that to convert from moles of oxygen to grams of oxygen. There's a simpler way to do this, and it's why I've tried to get you to do conversion factor method, because we can do this as a single step. We're going to go from 501 grams of heptane. We'll first convert from grams of heptane to moles of heptane. Once we have it in moles, then we can switch to a different species of chemical. We'll switch to moles of oxygen, and now we have it in oxygen. We'll solve what we asked for, was grams of oxygen. Molar mass, that's always going to be a 1. This was 100.2. This was 32.00. From our balanced chemical equation, 1 mole of heptane reacts with 11 moles of oxygen. Grams cancel grams, moles cancel moles, moles cancel moles, left with grams of oxygen. Do all the math. 501 divided by 100.2 times 11 times 32, I get 1,760 grams of oxygen. So you can see the benefit of conversion factor method, because we can do it all in one step. As these get more challenging, there'll be even more conversion factors you have to add in. The one thing to note is that if you do it as a multi-step process, do not round off until your final answer. If you do it as a single step, your final answer is the only value you'll get in the end. At this point, this should all be review for you. You've done all of this in your chemistry classes. Perhaps I've given you a different perspective to help you understand it. There's a large number of practice problems here. We're starting at practice problem 4, as we're continuing on from our last lecture. We have 4, 5, 6, 7, all the way down, tons of practice problems. And in the end, I have the correct answers here. Notice these right here. These are the coefficients for your balanced chemical equation. Please don't look at this until after you've done the problem. You can see if you've done it correctly. So at this point, you should pause your video and give these a try on your own. Take some time. This is the most important math for the laboratory. If you're unable to learn how to do this, find another career. The answers are all at the bottom. When you're done, I'll take a few of them up. For the rest of them, if you have issues, speak to me outside of class or ask me during tutorial. Give these a try now. I'd like to take up question 6. Ammonia is used to make fertilizers for lawns and gardens. This is used by reacting nitrogen from the air with hydrogen to make ammonia. Please note that the vast majority of the air you're breathing is not oxygen, it's nitrogen. This nitrogen is not bioavailable, meaning it can't be used out of the air directly as nitrogen in your body. What has to happen, it has to be fixed into an organic molecule, such as ammonia. In our foods, this is normally done by plants called legumes. In their root system, they have a symbiotic relationship with a microbe, and it fixes nitrogen for that plant. We can then eat that plant and get the nitrogen for ourselves. This is why often, when farmers have fields, in between growing one crop, they'll grow a legume, such as alfalfa. This will help naturally fertilize the soil. Now I bring this up because now we can actually use fertilizers. Please note that studies suggest that the carrying capacity of planet Earth, that means the number of humans that can live here with enough food, is only at 2 billion people without fertilizers. As a result, fertilizers are very important to sustain our large growing population. Science can be quite boring if you just do the math and the science. I would advise you to look into the scientists themselves because some of their stories are very interesting. The story of how fertilizers came about is a very interesting story. The process of fixing nitrogen, taking nitrogen from the air and reacting with hydrogen to make ammonia, this is called the Haber process. This is named after a scientist by the name of Fritz Haber. I would advise you look him up. He has a very interesting past. He is at the same time the best human being that ever lived and the worst human being that ever lived. Let me explain why. So Fritz Haber was a German scientist. He developed the process of nitrogen fixation. As a result, we can make fertilizers. Consequently, he's a wonderful human being because as a result of fertilizers, we can now sustain a much larger population. Consequently, he's one of the greatest human beings that ever lived. At the same time, fertilizers can be used to make bombs. If you go to a supply store and you order too much fertilizer, the RCMP will come to your door the next day. That is not a joke. This process was used to make many bombs during the war. During the First World War, he was instrumental in developing chemical warfare. He himself would go on the battlefield, and when the wind was right, he would open up canisters of chlorine gas so that it would blow towards the Allies and kill them. It's one thing to develop the technology, it's another thing to do it yourself. As a result, he's one of the worst human beings that ever lived. Science can discover many amazing things. It's what we do with those things that's important. We have to think about it ethically. We can do these things, but should we do these things? An example would be nuclear energy. We can create relatively clean energy using nuclear power, or we can create massive destructive bombs using the same technology. I would advise you look into Fritz Haber. Again, he was a German scientist during the First World War. He was looked on with high regard by the Germans at the time. However, when World War II happened, there was an issue. He was Jewish. Consequently, you can see where this might go. Again, the stories of some of these scientists are very interesting, and I advise you to look into it. I will plug a book right now. It's not my book. It's a wonderful book. It's called A Brief History of Nearly Everything. It's written by an author by the name of Bill Bryson. If you have some time, I highly recommend it. It literally is a brief history of almost everything, and you get some great stories in terms of science. Anyways, that's enough of your history lesson. Let's get back to the math and the chemistry. We're going to have to balance this chemical equation first. Here I have 2 nitrogens. Let's multiply this by 2. Now my nitrogens balance out. Here now I will have 6 hydrogens. To balance this out, I have to put a 3 there. Now my hydrogens balance out. Let's solve this now. How many grams of ammonia is formed when 1.34 moles of nitrogen react? So I'm going to convert from moles of nitrogen to moles of ammonia using the mole bridge, and then I'll convert to grams of ammonia using the molar mass of ammonia. For our mole bridge conversion, we use the coefficients that come in front. Here we have a 2, and you don't see it, but there's a 1 there. So every time 1 mole of nitrogen reacts, it creates 2 moles of ammonia. Molar mass, it's always going to be grams per mole. What's the molar mass of ammonia? Nitrogen is 14.0, and hydrogen is 1.008 grams per mole. Multiply that by 3, add those together. I get 17.034. Going to use 4 significant digits, 17.03. Moles of nitrogen, cancel moles of nitrogen. Moles of ammonia, cancel moles of ammonia. I'm left with grams of ammonia. We do the math now. 1.34 times 2 times 17.03. Significant digits now. These values come from our balanced chemical equation, therefore they are exact. This value here is also exact. We have 3 significant digits here. We have 4 significant digits here. Therefore 3 is the lowest. We're going to round off to 3 significant digits. This is approximately equal to 45.6 grams. And when you write the final answer, don't just include units, include the species of chemical as well. 45.6 grams of ammonia. Let's try the next one. How many grams of nitrogen is required to form 1 kilogram of ammonia? So here we have an extra step here. Let's write our plan. We'll start with kilograms of ammonia, When we use our molar mass, it's grams per mole. So we have to convert from kilograms to grams. Once I have it in grams, I can then convert to moles of ammonia. And then I can switch to a different species using the mole bridge. Finally, convert to grams of ammonia. So notice there will be 1, 2, 3, 4 conversion factors. Write down what we're given. 1 kilogram of ammonia. Going to go from kilograms to grams. 1 kilogram is 1,000 grams. We will then go from grams of ammonia to moles of ammonia. We will then go from moles of ammonia to moles of nitrogen. And lastly, we'll go from moles of nitrogen to grams of nitrogen. Many steps. I can fill some numbers in. Molar mass, it's always grams per mole. So that 1 is always going to be with the mole. From before, we calculated the molar mass of ammonia, 17.03. Nitrogen, nitrogen has a molar mass of 14.01. 2 nitrogens, 28.02. Go to our balanced chemical equation now for these values. N2, NH3. So 1 nitrogen for every 2 ammonias. 1 nitrogen, 2 ammonias. Do the math now. Kilograms cancels kilograms. Grams cancels grams. Oh, make sure that's the right one. Ammonia cancels ammonia. Moles of ammonia cancels moles of ammonia. Moles of nitrogen cancels moles of nitrogen. I'm left with grams of nitrogen. Now we do 1 times 1,000 divided by 17.3 divided by 2 times 28.02. Round this off significant digits now. Exact number, exact number, exact number, exact, exact, exact. I have 3, 4, and 4. Going to round this off to 3 significant digits. That's a 6, so it rounds up to 823 grams of what? Of nitrogen. Final answer. I'd like to now help you balance question number 8. I'm going to start with chlorine. I have 3 chlorine here. I have 1 there. So to balance that, I put a 3 in front of that. Now my chlorines are balanced. I will then work with my oxygens. Here we have 1 per molecule, but there's 3 of them. So to balance that out, I have to put a 3 here in front. Now my oxygens are balanced. Next up, I'm going to balance my nitrogens. I have 1 nitrogen here and I have 1 nitrogen here. So I can put a 1 there and there. Finally, I want to balance my hydrogens. On this side, I have 6. Here I have 3. And here I have 3. As a result, they're now all in balance. Let's double check each side. 3 chlorines on this side, 3 chlorines on that side. Chlorine is balanced. Oxygen, I have 3 oxygens on this side, and I have 3 oxygens on that side. They are balanced. Nitrogen, I have 1 nitrogen here, and I have 1 nitrogen there. They are balanced. And lastly, hydrogen, I have 6. 3 plus 3 is 6. Therefore, hydrogen is balanced. So here's my balanced chemical equation. When balancing chemical equations, quite often we leave the hydrogen or the oxygen to the end. You'll learn more about this in your chemistry class. Let's take up A together. How many moles of ammonia are required to produce 275 mils of water? So what's my plan here? I'm given mils of water, and I want to get to moles of ammonia. How do I go from milliliters to moles? Well, remember, we're dealing with water here. In the laboratory, this would be pure water. Because it's pure water, I can go from milliliters of water to grams of water. 1 mil of water is 1 gram. That's the density. I can then go from grams of water to moles of water, and then go to moles of ammonia. Simple as that. Let's do that now. 275 milliliters of water. 1 milliliter of water is 1 gram of water. Please note, you must show me this step. Don't just magically change the value from mils to grams. Show me the conversion factor. Then I can go from grams of water to moles of water. Using the mole bridge, I can go from moles of water to moles of ammonia. To convert from grams of water to moles of water, we'll use the molar mass. Molar mass of water. Oxygen is 16. Hydrogen is 1.008 times 2, 18.02 grams. In terms of our mole bridge, we'll use our balanced chemical equation. 3 moles of water reacts to create 1 mole of nitrogen. Cancel out values now. Milliliters of water cancels milliliters of water. Grams of water, grams of water. Moles of water, moles of water. 275 divided by 18.2 divided by 3. Significant digits now. Exact, 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 exact. I have 3 significant digits, and I have 4 significant digits. So 3 significant digits is what we're going to round off to. 5.09 moles of ammonia. Final answer. You should be able to do the remainder of the problems with all the knowledge you have now. So again, when converting from grams to moles or moles to grams, we use the molar mass. When converting from moles to atoms or molecules, or atoms and molecules to moles, we use Avogadro's number. When switching between 2 species of different chemicals, we require a balanced chemical equation. We use those coefficients in the balanced chemical equation to convert. As you can see, we've brought in metric conversions as well as density conversions. The rest of your stoichiometry you'll get from chemistry class. I'm hoping that this has reinforced the concepts you've already learned or presented it in a slightly different light to help you understand it on a deeper level. Understanding stoichiometry and doing it effectively is one of the most important laboratory skills a student can learn in a first-year science program. That's all for today. Until next time.